Hey physics fans, this is day I don't know what, but this is a unit starting on momentum and impulse. So today we'll learn a little bit about both of those, and another day this week we'll get to the conservation of momentum. So as you notice, there's already an egg toss competition. Hopefully you've already done the egg toss with somebody maybe in your family or so. Before we start this, it'll help make more sense of what you did with your egg toss. So here we go. So momentum. We're going to find out that, well, first of all, so what's momentum? You got a roller skate and you got a truck over there. So momentum is mass times your velocity. So it does have to do with motion, but remember, kinetic energy is 1/2 the mass times velocity squared, not the same thing. Because we have mass, which is a scalar amount, times velocity, which is a vector, and a mass times a vector is always a vector in that direction. So now we're talking about not scalar amounts like we did with work and energy, but we're talking about vector amounts that have to do with motion. Okay, so momentum is a measure of both the inertia, which is the amount of mass, and how fast the thing's going. It's a combo of the two. So we use a P because M's for mass, V is for velocity. P is silent like in momentum, but P, lowercase p, is what we use for momentum. Okay, so if the direction is not a big thing, you could just do mass times the speed, but in reality, momentum is a vector amount, and it is in the direction of that velocity over there. So I guess the point is, you can have a really large truck and a skate. Can they possibly have the same momentum? Well, sure, if they're not moving, they both have zero momentum. Or if the truck is moving really slow and the skate's moving really fast, it turns out, yes, look at that, they can actually have the same momentum. Isn't that special? Okay. So the question, what circumstances would a roller skate and truck have the same momentum? Something with really small mass can have a lot of momentum. Like a bullet, it's just got to be going really friggin' fast. So as long as the roller skate is going really fast and the truck is really slow, they can have the same amount of momentum. If they have the ratio of the speed as the same as the ratio of the masses, but inverse. So a 1,000 kilogram truck going really friggin' slow at 0.01, that's not a lot of momentum for a big truck. It can have the same momentum as a 1 kilogram skate going at 10 meters per second, which is about 20-some miles per hour. Alrighty. Oops. I should let that go in there. Alright, here we go. And I missed it again. One last time. Okay, it's slow, but I'll do it for the 5th time as a charm. And there we go. Then zoom, it's off. Alright, we wasted precious seconds on that. Impulse. So we have to learn about how things get momentum. We learn about how things get energies by you do work on something to change one kind of energy to another kind of energy. Well, things can get momentum and lose my momentum in terms of an impulse. Just as things gain kinetic energy and lose kinetic energy by doing work, we can gain and lose momentum by a term called impulse. Okay? So momentum changes is because there's a change, whether it's mass or velocity or both. There's definitely a change going on. A lot of times our mass isn't really changing. So usually it's just our velocity that's changing. Like in your car, you're really not changing mass that much, even though you're burning a little bit of gas as you drive the thing. You're not changing mass by that much, but your speed sure is changing. Okay? So normally changing momentum is just your velocity change, not always. Now, we already learned about the FMA thing. It turns out this whole unit is all about the FMA. We're going way back to Newton's laws of motions, and you guys did awesome on that, so you ought to do awesome on this unit. It's actually the same topic. It's just we're going to look at it a little bit differently. So instead of the acceleration, we're going to break this down into a change in velocity per time here. Okay? So we're going to apply a force over a period of time to change the momentum. So force times time is what we're going to call impulse for now. And it is a vector amount because that's a vector, time is a scalar, and a vector times a scalar is indeed a vector amount. So an impulse gives or takes away momentum, and it's going to be directional. I is for current in electrical systems, so J is the next letter. Gympulse. So force times time is gympulse? Not so much. But here's the point. A force equals your mass times your acceleration. Your acceleration is your change in velocity per time. So you're actually looking at FMA. It doesn't look like it maybe right now. It's not obvious. But if you divide the t on both sides, v per t, that is your acceleration. That's FMA. So everything we're learning here, we're taking off of the FMA stuff. Okay? So it's really nothing brand new. Here we go. Got something happening here in a second. Eyes up. So an object at rest has momentum. Why? It's not moving. Okay? Anything times 0 is 0. So to increase the momentum, you got to apply a force to that thing. And the longer you push on that thing, the more momentum it gains. That's why a pitcher, when it takes the ball, doesn't toss the ball just like this. That isn't pushing very long. You take it from way back over here and you throw it way back over there for a very long time. The longer you push on that, the faster it goes. You should have found the same thing about your egg toss competition. The longer you push on that thing, the faster the egg goes. And as you get further and further apart, you got to throw it faster. It's got to have more momentum. You have to push on it for longer. So pushing on it for a longer time for that force gives it more momentum. Pulling a slingshot. The further you pull it back, oh, there's a golf ball. Slow motion there. You pull a slingshot back, the further you pull it, the longer it pushes on it, the faster it goes. Same thing with the bow and arrow or a longer cannon. The longer the cannon you have, the faster that thing comes out. Or a rifle versus a pistol. A rifle has a longer barrel. It pushes on it for a longer period of time. It leaves the barrel much faster than a pistol. So something that's a short pistol, it can't shoot things very fast because it's not pushed on very, very long. Hitting a golf ball or baseball. When you hit a golf ball, you follow through. The reason you follow through on thing, maybe I'll back up on that, see if we can get that one more time. Oh, and here it comes. The longer you're pushing on that ball right there, it wasn't a very good follow through, but the longer you're pushing on that thing, the faster that ball is going to come off the club head, whether or a baseball bat or whatever. Okay? So the longer the time of interaction with that force, the bigger the impulse. All right, or the bigger the change in momentum. So a little bit of vocab here. Impulse is your force times your time, but it causes the change in momentum. Okay? So the bigger the impulse, the bigger the change in momentum. What's confusing to many people is the impulse and the impact. They sound very similar, but they are in fact different. Impact has to do with only the force, only the amount of force. Impulse is not just the force. It's the force and the time. It's the combo there. Okay, so impact forces is only talking about the average force pushing on something, not the impulse. There's two different meanings. They look very similar, but they're actually two different meanings. One's over a period of time, one's just the actual force. Here we go. Decreasing momentum. Would you rather be in the brown car or the blue car? Because one hits the hay, one hits the brick wall. Which car do you want to be in? So which is more safe, huh? Alrighty, look at there. Alright, so of course it looks like the hay is a better result because that car is all crunched up and so is your face in the front of that windshield as you smack that wall. So they had the same momentum. They both stopped. They both indeed had the same change in momentum. So if they have the same change in momentum, that means the impulse is actually the same. So why does it matter which one you hit if you have the same impulse? Well, in each case, momentum is decreased by the same amount, so the same impulse. They both pushed backwards, had a negative impulse, negative force times the time. This negative impulse decreased the momentum the same in both cases. But the haystack extended the period of time which is brought to 0. So if I back up this truck a little bit, if you notice, it's the same F times T. Here's a little f, big fat T. Here's a big fat F, little tiny t. So there's a much greater force on the blue car because it took such a small time to stop. Whereas hitting the haystack took a long amount of time to stop, therefore decreased the force. So you should have noticed in catching that egg in the egg catch competition, if your hands move with the egg, you're still stopping the egg, but that's like the haystack. You're making it a long time to stop that egg, actually decreases the force on it. But if you had your hands moving forward when you caught that egg, that's what caused those things to break. Because it's a very small time to stop the egg makes a very big force. It's the same impulse on the egg, whether you caught it with soft hands like the haystack or hard hands coming towards the thing. It's the same impulse, but one has a smaller force, one has a greater force because of difference in time. So timing is indeed everything. Okay. So hitting the haystack extends the time, still the same change in momentum and the exact same impulse. They both stopped the car. Both had the same impulse, but the haystack had a smaller impact force. So the force was smaller on the haystack, but the impulse was exactly the same because they both had the same net. They both went to zero. So the deceleration was less in the haystack, meaning a smaller force, because it took more time to stop than it did the wall. Okay, so what if you ever want to decrease the force of an impact? You extend the time of the thing. Same thing with your cars. Cars are much safer than they used to be. Cars are made so they actually crumple when they hit things. This front end here is made to crumple, because when you smack something head on, it takes more time to stop. It makes it a lot safer for the driver. You also have one in the back. A lot of people get rear-ended because you're on the phones texting and you don't see somebody stop, then you crumple into somebody else and everybody else is crumpling into you because you didn't see what was going on. And the other big thing is even side impacts are pretty dangerous as well. So they're doing some things in the side impacts to make it reinforced here so you can't penetrate the side on if you get T-boned. Sure, there's some airbags, but the airbag kind of serves as a timing thing as well. Two things for the airbag. One, it's not just one little point smacking you like it's the steering column smacking you in the chest. You spread out the area. But the other big thing, it makes it more time to stop your body. By making it more time to stop your body, by having this cushion like there, it doesn't change the impulse, it changes the impact. The force is smaller because the time is longer to stop, is the idea. Alrighty, here we go. Clicking through. Clicking some more. Doing a lot of clicking here. Alright. And we got the same. And there we go. Whew, that took forever. So, hey, there's old Bruno. They're about to get smacked in the face. He's been smacked in the face a lot, you can tell. So what could Bruno do if he knows he's getting smacked in the face so it doesn't hurt so darn much and doesn't get such an ugly looking face because he gets smacked all the time? There it is, Bruno unboxing. You notice what he did there, everybody? So he knew he was getting hit, but what did he do with his head? He moved it backwards. That's the old soft hands idea. You're pulling your hands backwards and catching the egg. You still have the same impulse, but the longer the time, the smaller the force. That means the smaller the change in momentum for his head, smaller change in momentum of his brain, less brain injuries that way. If you're moving, that's called rolling with the punches. If someone's going to smack you, you roll with the punches. Jaw locked together, because if you're locked together, you're going to move the whole mass, which is a much bigger mass than just your jaw. Jaws are easy to break because they're a low mass. So always have your jaw. That's why you have a thing in your mouth so you can clench up when you're playing sports. If you do get hit in the head, you don't break your jaw. But the point is, if you move with it, whether you're in football getting tackled, if you kind of go limp and go with the thing, that extends the time of the tackle, makes the actual force smaller. As opposed in this case where Bruno's going towards it, that's how your egg broke. If your hands are moving towards the egg, that makes for a very large force because the time of impact is so small. It takes just such a small time of interaction. So that's really dangerous on the face and the brain. Here's old Barney Gervais on a bungee jump. Well, what would happen if there's no flex in this cable? That would mean a very small time to stop old Barney Gervais at the end. Huge friggin' force. But by having a flexible cord that makes the time very long and the force smaller and makes it a much more pleasurable event in doing the old bungee jump. Okay, so same idea here. So by making it take longer to stop, it doesn't change so much the impulse, but it makes the time last longer, making the impact or the force smaller actually on the body. Okay, because it stretches for a long time, the average force is much smaller. All right, now we're going to do some questions. I'm going to pause because I can't get all the questions in here. We're at about 14 minutes, and I'll come right back with the second video.